Hello, my name is Yan Li. Today I'm going to present our work on reinforcement learning enabled seamless microgrid interconnection. This is a collaborative work between Penn State University, Eversource Energy, and Rhythm Techniques. If you have interest or questions about our work, we are more than happy to discuss details with you. So first of all, let me briefly introduce our research motivation. Why we want to connect microgrids together. We know resilient operations of electric power system has become one of the major concerns in power engineering. And one promising solution is to connect multiple microgrids together to let them support each other and energize a large-scale area. So one question is how we can get the generic knowledge of the power of the point of common coupling so that we can correspondingly control distributed energy resources for automatically connect one microgrid to its neighboring system. In this work, to solve this problem, we propose a reinforcement learning enabled microgrid interconnection method. We call it RL-MI. So this technique integrates reinforcement learning method into distributed energy resources controller and system operations so that our system could be enabled with learning capability. And then the system can be automatically adjust its DR output and connect its neighboring systems. So in future, we can also enable bulk power systems restoration by using microgrid in a bottom-up way. So here is the brief introduction of our reinforcement learning enabled DR controllers. And briefly talking about, so here we have 4 blocks in the controller. The first one is frequency restoration. That means when we install a system, so we're going to eventually restore the frequency to the nominal frequency. And then we have a voltage angle adjustment and voltage magnitude adjustment. And their input is from the Q-learning block. The function of Q-learning is to adjust a DR output voltage angle and amplitude so that we can have the voltage as a PCC meet the interconnection requirement. So this is the brain of our controller. And more specifically, in our work, we use Q-learning technique to calculate the voltage angle adjustment and voltage amplitude adjustment. Then we have a test example to illustrate our idea. So here we use a typical networked microgrid system. We have 6 microgrids. Circuit breaker 0 is open so that our microgrid is operating in the island mode. And the first 2 graphs show you the operations where we don't use the reinforcement learning enabled control system. So at 0.0 second, we directly close the circuit breaker 1 and circuit breaker 2 so that we can interconnect microgrid 1 to microgrid 2. From the simulation result, you can see after we interconnecting the system, we couldn't maintain a stable operations. The reason is given in figure 2, because before we close the circuit breaker, there are too much difference between their voltage. And then the third one and fourth one show you the result when we use the reinforcement learning technique. So we also close the circuit breaker 1 and 2 at 0.5 second. So from this result, you can see by using the reinforcement learning enabled control system, we can quickly adjust the output voltage so that we can meet the interconnection requirement. And the last 2 figures show you the reinforcement learning result. And the left figure shows the amplitude training result, and the right one shows the voltage angle result. So here is our conclusion. So we propose a reinforcement learning enabled microgrid interconnection method to seamlessly interconnect microgrids through adjusting the output of DRs. And more specifically, we use the Q-learning method to enable DR controller with the learning capability. And then this method can also be used to restore the bulk power system in a bottom-up feature in the future. Thank you.